All good.
Perfect. So thank you very much, Vincent. And first of all, I'm honored to be here. Thank you for having me today. And I'm going to talk about dense retrieval with Apache Solr, neural search. So a very short introduction about myself, because Vincent already gave it one, so I will be brief. So my name is Alessandro Benedetti. I'm Italian, but I'm based in London. And I was born in Tarquinia, which is an ancient Etruscan city in Italy, which is actually a pre-Roman civilization. So like 3,000 years ago, more or less, my birthplace, a little bit more potentially. I'm an R&D software engineer and director at SIS, and I have a master's degree in computer science. I am the program committee members of various international academic conferences because I'm quite active in the community, and I do review for papers for the European Conference on Information Retrieval, the Special Interest Group on Information Retrieval, and the SIRES, which is a new conference that go biannual about design of information retrieval systems. I'm an Apache, Lucene, and Solr committer and PMC member, and I've been working with Elasticsearch as well for many years. So my passions are about information retrieval and integrating artificial intelligence and machine learning techniques with information retrieval to improve the user experience. In my spare time, I love to play beach volleyball when I go back to Italy during summer and snowboarding during winter. So about SIS, my company, headquartered in London, but we are distributed as a company. So we have people in Qatar, Spain, and Italy. And we are open source enthusiasts. So we work with open source, but we also contribute back to open source. So we support the Lucene and Solr mailing list. We evangelize our research and works and contributions to conferences and meetups. And we also give back code. The Apache neural search contribution is one example of it. So we feel that it's the right thing to do ethically to also guarantee a steady progress in the field. And for this reason, we are also working like on hot topics. As Vincent said, neural search now is incredibly hot and is an area we are exploring. Recently, we are exploring this a lot, but we've been working also on natural language processing integrations with information retrieval, machine learning integrations such as learning to rank to improve the ranking capability of an information retrieval system. And then we also been focused on relevance tuning, document similarity, and then, in my opinion, one of the most important topics of all, which is search quality evaluation. So measuring the quality of your search engine to effectively measure if you are achieving your expectations and if you are satisfying your users and your business stakeholders. So this is an overview of the agenda for today. We're going to start describing the problems that affect the semantic search domain. So semantic search is quite a buzzword. It's a sort of holy grail for information retrieval systems. So having a system that is able to understand the semantic of the user information need, the semantic of the corpus of information, and it always returns you relevant results, suppressing unrelevant results. So nowadays, there are problems. It's an open problem, so it's not been solved yet. So we're going to first explore some of the problems that affect this approach to search and how neural, which we can also say vector-based search, aims to solve this problem. After that, we are going to dive in the Apache Solr implementation to functionally obtain neural vector-based search with an open source system. And then how you can integrate large language models with the Apache Solr module for neural search and obtain an end-to-end neural search. And my colleagues are currently doing. So let's start from the semantic search problems. So One of the most important problems in the domain of semantic search is the vocabulary mismatch problem. The vocabulary mismatch problem happens when the lexicon of the user information needs differs from the lexicon in the corpus of information. So currently, the user expresses his own information need through a set of keywords or potentially a natural language request. How many people live in Rome? So this query is about the population in Rome. So the user is attempting to gather information about the population of the city of Rome. So there are, in the corpus of information, there may be many documents related to this topic. Probably one of the best documents would be Rome's population is 4.3 million people. Now, these documents share one keyword with the user information need query. And yeah, from the user perspective would be perfectly relevant. But for a lexical information retrieval system, another document, such as hundreds of people, so one of the keywords, queuing for live, another keyword, music in Rome, another keyword. So we have an intersection of 3 query terms from the user query, and these will end up as a false positive, much likely. So in a lexical information retrieval system will recognize this document to be more relevant than the other document, which is Rome's population, which is effectively satisfying the user information need. Another example of vocabulary mismatch problem is with false negatives. So if we run a query and is relevant for the 2022 Year of the Tiger from the Chinese calendar, how big is a tiger? We may have a false negative from our corpus of information because the lexical information retrieval system is not able to recognize the scientific Latin name of the tiger. So a document containing the tiger is the biggest member of the Felidae family, which contains 2 of the query terms. Of course, biggest will require some stemming, but it's a problem that has been solved many years ago, so it's quite common for nowadays information retrieval systems to be able to recognize like biggest as something related with big. Another document containing Panthera tigris can reach 390 centimeters nose to tail, unfortunately, won't be returned because the system, unless you manually configure some synonyms configurations or anyway you integrate it with some synonyms mechanism, is not going to be able to recognize that Panthera tigris is the same concept of tiger. So we've seen false positives and false negatives can be caused by the vocabulary mismatch problem. In general, this is a matter of semantic similarity. So there are queries that express user information needs that are lexically very, very similar, such as how are you or how old are you? So literally just one query term in difference that have a completely different semantic. And we may have the opposite as well. So queries that share pretty much nothing from a query term perspective, such as how old are you and what is your age, but that are semantically equivalent. So neural vector-based search aims to solve this problem. And before we dive into this topic, let's digress a little bit and explain how in information retrieval we may represent query and documents as vectors. We have in here 2 main different approaches. sparse vector representation and a dense vector representation. So the sparse vector representation is the most popular, is effectively been there for a while, and is the representation used in the bag of words approach, which is one of the most common lexical approaches in there. So if you have an information retrieval, a classic information retrieval system that does query term matching, is very likely going to use a bag of words approach and a sparse representation. In a sparse vector representation, each term of the corpus dictionary is one vector dimension. So the number of dimensions of the vector representation of the user information need or the document is the term dictionary cardinality. Effectively, for any given document we are representing, the vector contains mostly zeros and ones, or potentially the term frequency, so how many times that term appears in the document or in the query, for the terms that are in the document and the query. And normally this is a subset, a small subset of the entire term dictionary of the corpus. So that's the reason it's called sparse, because the document vector or the query vector will be pretty much all zeros, and then only few elements of the vector that represents the term in the document or in the query are going to be different from zero. On the other end, with the advent of machine learning and neural representation and neural network and deep learning based solutions, we ended up with a different way of representing text effectively. And this is the dense vector approach, which means we fix a number of dimensions. And normally, this cardinality is much smaller than the term dictionary cardinality. And the vector for any given document is effectively inferred by our neural network system, potentially a deep neural network. So with this approach, the vector for any given document will be quite the opposite of the sparse representation and will be contain mostly non-zeros elements. But if it's easy to understand the bag of words approach and how you can generate a vector out of text representation, but how can we generate such dense vectors? At this point, we have the neural side of neural search. We train our neural network-based model with labeled samples. We transform text to vectors using the weights extracted from the neural network. And then at query time, we do the same for the query. And then we do a vector lookup in the index. So this is a summary, an overview of the neural search workflow. So we have an input document and we have an input query. We use a transformer. So we are going to go back a little bit on transformers later on, but for the sake of this piece of the presentation, you can consider the transformer as a component able to infer. We'll see later how, I'll give an introduction. Of course, we are not going to go too much in depth about this, but just to give you a little bit of context. And then this component is able to effectively encode document text to vectors and query text to the query vector. Then the document vectors are going to be indexed in appropriate data structures that allow efficient retrieval. And then at query time, we are going to be able to execute a k-nearest neighbor search that, taking in input the query text, transformed and encoded in a query vector, is able to return the k-nearest neighbors in terms of a certain distance in a vector space from the query. So effectively, the similarity between a query and a document that in lexical information retrieval was calculated, for example, as a BM25 score, is now translated to distance in a vector space. But what kind of distance? So from high school and university, you may be familiar with some of these distances. So we studied in geometry, and at the time, it was probably not that clear how this could be used like in real world information retrieval, but effectively, since we are representing documents as vectors, it's quite natural to express a relationship between documents that now are vectors in terms of distance. There are various distances, and to be honest, there's no single distance that rules them all. So you need to experiment, you need to effectively test on your data set which of the distances between vector is a nice fit for you. Now, in information retrieval, it's been quite common to use cosine similarity as a standard distance, which is a normalized inner product between vectors. But to be honest, if in your case, for example, Euclidean distance works better, if you set up a search quality evaluation system that guarantee these benefits, it's absolutely fine to use a different kind of distance. So this distance effectively just calculates how far a vector is from another. And closer vectors means closer semantic between the texts. Nearest neighbor retrieval is a technique that allows you to retrieve from your corpus of vectors the closer vectors, so the higher semantically similar vectors to your query. And the relevance score is between your query and documents is calculated with a vector similarity distance metric, who are, for example, the cosine similarity, or the Euclidean, or any of the others. What is the problem with nearest neighbor search? That running exact nearest neighbor search is quite expensive because you need to take the vector for the user query, then the vector for each document, and calculate the distance. So you do a 1 versus 1 similarity calculus for all the documents in the corpus. And this can be, millions, trillions of documents. So it's very expensive. Do we really need an exact distance calculation between the vectors to retrieve what's relevant? So do we really care if the score is a cosine similarity of 0.98 or 0.9 is enough? Now, the answer is it depends, of course. So there are domains where you can't accept an approximation, but there are other domains where it's perfectly fine. And actually, most of the time, it's absolutely fine to lose some accuracy if you get a massive performance boost. For this reason, researchers across the world started to think how to pre-process the data sets and build some kind of index data structures, right? I mean, in lexical information retrieval, the index approach, the inverted index approach is quite common. So, you spend time at indexing time offline to build data structures that will help you at query time to have fast search. So the mechanism was pretty much the same. So let's pre-process the data, let's build some data structures offline, and then even if we lose a little bit of accuracy, we're going to get a massive performance boost at query time. Now, generally, this means to lose a little bit of information, to compress information, and model them in dedicated data structures. There are mainly 3 families of solutions and data structures that are nice and usable for approximate nearest neighbor search. tree-based approaches, which means that the vector space is partitioned with a K-tree representation, so where you branch depending on effectively a cut in the vector space. And then at query time, you just navigate the tree and you don't explore the entirety of the vector space, but you just go evaluating conditions and navigating just a portion, a partition of the vector space. So in this way, it's cheaper to run queries. Another approach is based on hashing. So hashing means you try to reduce the dimensionality of your vectors, preserving the distances in a sense that you group similar objects, so you're approximate, but still you preserve enough difference to guarantee a nice search experience. I left in the slides that I will share with the organizers of the meetup some pointer to like Wikipedia or interesting blogs that may explain you this more in detail. Another approach, and this is the approach we're going to be focused on today because it's the one implemented in Lucene and Solr, is graph-based approach. So building a graph to represent the relationship between vectors in terms of distance. And specifically, one solution which is implemented currently in Lucene, and the only solution that is implemented currently in Lucene and Solr, is hierarchical navigable small world graph, HNSW. So HNSW stands for hierarchical navigable small world graphs, and it's one of the top performing solutions that builds an index time data structure to satisfy an approximate nearest neighbor search. I left in here the references to the two papers that explore the techniques from 2015 and 18. And how does it work? First of all, hierarchical navigable small world graphs are proximity graphs. So vertices are vectors, and links means vectors that are close in the vector space. The hierarchical is because there are a set of layers. So this is an approach similar to the skip list approach, where in the higher layers, you want fast retrieval. So you enter your search from the higher layer for the highest layer, and you have longer edges. So in the highest layer, effectively, you have a less number of vertices, and they are linked with long edges. In this way, you can quickly identify an interesting point, and then you can dive in the lower layers, which are for accuracy, where edges become shorter and shorter. You effectively find a local minimum per layer, and then you go down and you explore the neighbors of this local minimum until you reach the final layer and potentially find the global minimum. Now, of course, there is an approximation. And this approximation means that you may have a degree for your vertices that depends on parameters at building time. So you may set a higher number of connections between your vertices. This means you will lower the probability of hitting a local minimum. So it's more likely you will get a global minimum when searching. But of course, it's more expensive because the more the links between the nodes and the more the nodes, and effectively, the more expensive your search. So all of these are parameters that are exposed in Solr, and also in this case, there is no silver bullet. So I mean, there are defaults which work quite fine, but if you want like to fine tune the solution for your data, I would recommend to experiment and assess different approaches in building, different hyperparameters in building, and checking how these impact your quality. So how this is implemented in Apache Solr. First of all, Apache Solr is an open source project from the Apache Software Foundation that includes Apache Lucene as the main information retrieval library used. Apache Lucene and Solr used to be a single project for many years, actually, from 2010 till 2021, effectively. And they split effectively quite recently again. So now they are two separate projects within the Apache Software Foundation, so they are quite coupled together. So let's start from the Lucene implementation, because the goodies of hierarchical navigable small world graph comes from the internals of Lucene. In November 2020, more or less, it was still an open problem how to run vector-based search in Lucene. There were transformers to get like decent vectors out of text, but it was quite hard to search them using Apache Lucene as an open source solution. There were like some vector representation in Lucene exposed to like dog values, to like potentially payload of terms, but those data structures were not designed for nearest neighbor search. So it was possible to do that, but it was not really built on a dedicated data structure and infrastructure. With Lucene 9.0 in November 2020, a dedicated file format, so a dedicated codec in Lucene, was introduced for navigable small world graph. So now it was possible to run native nearest neighbor search in Lucene using dedicated data structures. Now, from November 2020 until now, many other contributions have improved the solution, introducing various aspects that improve nearest neighbor search. The major improvements are listed in this slide, but you can find all the improvements, all the work in relation to vector-based and neural search in Lucene with the link, the Jira link I will present you in the slides. So what has been like in the route to a comprehensive neural search, what have been like the most important steps? For sure, the handling of document deletions that happened in January 2022, the introduction of the hierarchy in hierarchical navigable small world graph, because originally it was just one layer implemented in Lucene, and now it's hierarchical, and it's available from Lucene 9.1. The reuse of many data structures to improve both performance and memory footprint for the nearest neighbor search in March 2022. And finally, the pre-filters capability with k-nearest neighbor search also released with Apache Lucene 9.1. So what's the biggest problem with pre-filters? Originally, in Lucene, it was only possible to post-filter results coming from neural search. So this means that you find the top k nearest neighbors, and then you apply your filter. So potentially you end up with 0 results or less than k results. With pre-filters, you first apply your filters. So you like filters potentially from your faceting that reduce the scope of your search, and then you run the nearest neighbor search on the subset of the results. So this is actually much better. In Lucene, there are 3 vector similarity functions implemented that are then exposed in Apache Solr: Euclidean distance, dot product, and cosine distance. Effectively, there is more difference between the dot product and the cosine distance. The cosine will normalize the dot product effectively. So effectively, if you have vectors that are of unit length, you can just use the dot product. It's going to be a performance improvement. If your vectors are normalized, go ahead with the dot product. If not, you can use the cosine distance. So this, of course, depends if you can pre-process. It depends on the nature of your vectors. With the contribution to Lucene, so this was something contributed mostly by Michael Sokolov, Maya, and other Lucene, Tomoko Uchiha, and various other contributors from the Lucene community originally, and then has been exposed in Solr by myself and my team. And I've been working also with the Lucene implementation, being an Apache Lucene committer. But this was like the main aspect of the contribution originally. So introducing KNN vector field. So a field that gives you the ability, and this is what is used in Solr, to index a vector. So pretty easy. We wanted this to be quite straightforward. So the field name, the values, and the distance. That's it. You don't need to express any other difficult parameter. And how this works from the coder perspective, so this is what is used internally in Lucene. So there is like a dedicated posting format for the building of the hierarchical navigable small world graph. And then there is both readers and writers that effectively rely on a graph builder and searcher. At query time, in Lucene, there is a KNN vector query that takes in input a field, takes in input a vector query, the top K parameter, and potentially a Lucene query as a pre-filter. So the KNN vector query and the KNN vector field are internally used in Solr to expose the vector-based search capability. This has been introduced with Apache Solr 9.0 and is available. The developments are being tracked in 1580, 880, and starting from the schema, we have a new field type. This new field type is called dense vector field, and as a standard parameters takes in input the vector dimension, which is limited to 1024 currently. This is hard-coded in Lucene just to guarantee performance and avoid people playing with like high values, but potentially would be, I mean, as we are more confident of the performance of the solution, we may effectively enlarge this value, or potentially if you want, you can change it in Lucene, build it again, and use it in your custom library or in your custom solution. The similarity function, Euclidean dot product and cosine distance, the one we saw in Lucene. And then there are two additional parameters that are quite advanced and then affect how you build the graph. HNSW max connections and HNSW beam width. Briefly, they match with parameters, hyperparameters described in the paper. So I would recommend to look at the paper to understanding them more. In a nutshell, they affect how dense is your graph, effectively how many links you build in your graph and the degree of the vertices and the amount of nodes in each layer. At indexing time, we wanted this to be as simple as possible. So if you use JSON to push data to Solr, it's literally just using JSON arrays. So for your vectors, just a JSON vector, a JSON array. If you use XML, this probably is more verbose, but you can express it as just multiple values for a specific attributes. Finally, in SolarJ, it's just a matter of using Java lists effectively. So lists of float values. So they are not different from like multi-valued fields effectively from an indexing perspective and a retrieval. So when you get back the result. At query time, there is a new query parser, the KNN query parser. Also in this case, we wanted this to be as simple as possible. So it takes in input, of course, the query parser name. So this is like standard Solr. A field name where you want to run your vector-based search, the top K, the neighbors, the number of neighbors you want to retrieve, and then the query vector. some observation and limitations. Filter queries, at the moment, in Solr, so with Solr 9.0, is just post-filtering. So as I said, there is an intersection between the documents coming out of the top K from the nearest neighbor and the subset of documents coming out of your filter queries. We are working on pre-filtering. Actually, we are pretty close to merge our contribution for pre-filtering. So this is coming with Solr 9.1. We are reviewing the pull request, and it's going to be merged probably in the next couple of days. For re-ranking, there's another limitation that at the moment is not a pure rescoring of the top K results you are re-ranking. So again, it's just an intersection between the top K you re-rank and the top K returned from the nearest neighbor search. Also in this case, we want to bring like a classic rescoring, and this is coming in a later release. I don't know if this is coming with Solr 9.1. We are working on this direction. Hopefully it will, but if not, it's going to come in the next, so probably 9.2. With Solr 9.0, one of the coolest things you can do is combine dense and sparse search. There are certain query parsers in Solr that allow you to effectively combine different types of clauses. You can combine them with like Boolean operators, for example, with the Boolean query parser. So like should clause 1, should clause 2. So you want document that match the clause 1 or the clause 2 and get the appropriate score. So this is doable. You express the clause 1 using a classic query parser, whatever you like. It can be a Dennis can be like a simple field query parser, Lucene query parser, whatever. And then you can combine it with the vector-based search. What will happen behind the scenes? Solr builds a Lucene query that is going to be a lexical query, so ID, for example, 901, combine issued with a KNN vector query. So this is quite cool. The scores will be summed. Of course, you need to be careful of how the score scale, because the score from the neural search will be from 0 to 1, while the score from your lexical search may be on a different kind of scale. So you need to make sure you properly assess that, but it's doable, it works. And we've done some initial benchmark just to have an idea. I mean, is it something usable? I mean, is vector-based search in Solr 9.0 usable? And we ran an experiment on a small data set of roughly 500,000 documents from, actually, yeah, mostly 500,000 documents from Wikipedia, and almost 6,000 queries from Wikipedia as well, and an average document length of 1,000 words, and like roughly 5 or 6, close to 6, actually approaching to 6 words for the average query length. And we noticed that the index time performance is worse, so it requires more time to build the graphs, but still usable. And query time is actually quite nice, because we have like actually faster queries for KNN on this data set, and even after index optimization, so when merging segments is even better. So when you are searching on just one segment contains the graph is better, and you get a much better margin than when you optimize for lexical search. Now, this doesn't necessarily reflect bigger volumes linearly, but it's encouraging. So it's like, okay, it's usable. I mean, we are going to repeat the benchmark also with like bigger data sets in the future, but it was like a great news. Like, okay, great. I mean, it's something that is usable also in production. But we were like at the beginning with a question like, how can we generate the vectors? So what's the component that produce vectors? So large language models need to be trained on a lot of data to be able to understand language and encode text in vectors. And normally this is quite difficult for the average size a company or enterprise or project generally. So transformers came to the rescue with a pre-training, a non-supervised pre-training on large corpora such as Wikipedia or the web, and then a fine-tuning for specific tasks like dense retrieval, essay generation, translation, text summarization, and similar. So you get a model that has been pre-trained on large amount of data, and then you fine-tune it to your problem. So how these models are pre-trained, some of them are pre-trained with masked language model approach. So you effectively mask a word for your input, and you train your deep neural network to predict the missing word. BERT is one of the most famous approaches. It's one of the most famous large language models from Google, and effectively represent information using a neural network with 12 layers and 760 dimensions. And there are like many different versions of BERT nowadays. So you will find like different dimensions and different training data and different also training approaches. But the most important idea is that it's pre-trained on large amount of data and then fine-tune on your data. To effectively, if we fine-tune it for dense retrieval, we want to reduce we want to effectively increase the gap between a non-relevant document and a positive document score. So we will fine-tune the weights of the BERT neural network to increase the distance between a document that is relevant for the query and a document that is unrelevant to the query. And I leave in here some example of code from PyTorch, open source code that you can use to encode your queries and text in vectors using sentence BERT, for example, to encode sentences in vectors. So we are going to skip this, but I leave the code in the slides. So what's the work we are currently working on? So first of all, we are simplifying the way you configure your advanced parameters and algorithm in Solr. So at the moment, only HNSW algorithm is supported, but it's exposed through like complex codec formats. And like most of Solr admins wouldn't even know what a codec is. So we are changing these from codec format, and you need to specify exactly the Lucene codec to the algorithm. So you will just express the algorithm, default HNSW, and then you specify if you want the fitted parameter for HNSW. In the future, there may be different algorithms supported. So there is already some work going on for IVF flat, which is hashing based, if I remember correctly, but anyway, it's like a different approach for hierarchical navigable mobile graph, and potentially in the future, many different algorithms can be implemented. As I said, working into contributing pre-filtering. So this is going to be like a massive improvement, especially for people that use KNN search in conjunction with lexical filters. And there is a Jira issue already there. And as I said, we are really close to the merge of the contribution. Another contribution that has been done literally yesterday, and today I will backport it to Lucene 9.x, which is going to be 9.3, is a simplification and improvement on the vector similarity function. The Euclidean distance works in an opposite way as the other similarities. So it was a distance. So like higher values means higher distance, while the cosine similarity and dot product higher values means higher similarity. So they were working the opposite. So I simplified that. And to make it all look into the same direction, and also some refactor of internal data structures to improve also some functional, like type breaking, when you have like the same score and you want to have like the same type breaking mechanism that is in Lucene. And another work we are currently progressing on is the native integration with BERT in Solr. It will be potentially not. So this means that you will be able to just run a natural language query and just push natural language documents, and Solr, appropriately configured, will do the inference. So you configure Solr with your BERT model, and Solr itself, or potentially an external service set in the configuration, will return the vectors for you and index them. So potentially, you wouldn't even need to run vector-based search explicitly. It will be run behind the scenes. So you just pass query text as natural language, you just pass documents as natural language, you configure Solr with your BERT model path, and then Solr will do everything on its own. Some additional resources for your curiosity. We wrote many blog posts on this topic, starting from the contribution itself, describing the contribution and the benchmark, through how you can use artificial intelligence to improve information retrieval in many ways. So using BERT, tackling the vocabulary mismatch problem, or using neural networks to expand your documents. So I want to conclude with some special thanks to the Apache Lucene community for all the HNSW implementation work. Elia Porciani, a colleague of mine that has been an active contributor of code for the Apache Solr neural search components. Christine for the accurate review of the pull requests, has been really valuable. And Cassandra and Michael for the review and correction of the documentation, which is now available in Solr, the reference guide. Being a non-native speaker, of course, it was very, very valuable. So I should be perfect in time, hopefully. So over to Vincent for the Q&A. And hopefully it was clear enough and you enjoyed the talk.
Thanks, Alexander, for the great talk. Like if you have questions, please raise your hand. I think there is already